All right, so VSEPR and bond hybridization. VSEPR structures, I had given you a chart in your packet. It looks like this. Yep. This year, you're going to have to memorize this guy. Okay? No, I'm not. So what you need to have memorized is bonding and loan, those two columns, and then the bond angle and the name. So bonding and loan, those first two columns. I don't know if you want to put a star there or something. The bond angles, put a star on that guy. And then the last one is geometry of atoms. Geometry of atoms. That's the last column you have to have memorized. So, 1, 2, 3. Okay. 1, 2. Yeah. Now, I will tell you that most of the time, the questions refer to everything above seesaw. Everything on here is fair game. But if you can't memorize the entire thing and you're like, I just can't devote that many neurons to this, then at least get above seesaw memorized. Okay? All right, so what is this? When we talk about valence shell electron repulsion, we are talking about Jacob or Nicholas, can you guys grab, there should be a bin up there or a bag that has some balloons in it. Could you bring those up to me? Okay, so VSEPR, VSEPR, as opposed to the church, which is VESPER. Okay. This VSEPR refers to valence shell, so that's the outer shell. Electron pair repulsion. Why would they repel? Same charge, like charges repel. Okay, so they're going to want to spread out as far away from each other as possible so that they can minimize that repulsion. Okay, and that then leads to this molecular geometry. So how do you figure out what shape it is? You're going to go back and you're going to draw your Lewis structures. You're going to count the bonds and the lone pair around that central atom or whatever atom they're referring to. They'll say the nitrogen or the first carbon, or they will indicate which one that they want you to talk about. And you will tell them then, based on those lone pairs and the bonds, what geometry it is. And that is why I have given you that chart to memorize. Okay? All right. Like I said, memorize this guy. Whoops. It does that to me all the time. All right. This is kind of a breakdown of that. A little different, but it's there. Why are you not advancing? There we go. All right, so let's draw some structures and figure out geometries. All right, so my phosphorus is going to be in the middle. How do I know that phosphorus is in the middle? First one listed, lowest electronegativity. Couple different reasons. Can phosphorus expand its octet? Yes. Okay. Phosphorus is 5 electrons. Chlorine has 6. It has 7 times 6, which is 42. And then notice this negative charge here. That means we have an extra 1 here. So that gives us a total of 48 electrons around this. Okay? How am I going to position those chlorines around? Yep, we're going to put them all the way around here. Kind of spread them out equally around. Okay. Right now, how many electrons do I have placed of my 48?
12.
12. Okay. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 26, 27, 28, 29, 30, 31, 32, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. Done. Yes?
Do you need to put that box around it?
Yes. Not done. Done. All right. So now we go to our handy, wow, our handy dandy chart. How many things do I have around my central atom? 6. Do I have any lone pairs? No. So this is octahedral with a bond angle of 90 degrees. Now, does this look like 90 degrees here? No. What's the difference? Why does that say 90 and this is...
Because it would be 3D, but this is on 2D.
Right. I've drawn a 2D representation of a 3D thing. Okay? And there's no way with my lack of artistry skills that I'm going to be able to draw that. It's just not going to happen, y'all. All right. Next one then. ICL. What is it? ICL3?
Yes.
All right. So I've got iodine and 3 chlorines. Each one of those has 7. So 7 times 4 is 28 electrons. So iodine's going in the middle. And I'm going to attach my 3 chlorine coming out of here. Okay. And I'm going to start placing my electrons. Right now I've got 6. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Chlorines are all filled. What do I do with those extra electrons?
You can add some of the iodine.
Yep. So I'm going to add lone pairs onto the iodine. Okay. Then I go over to my chart.
Is the iodine allowed to have charge?
Yeah, it could expand its octet. And it's typically the central atom that will expand the octet, not the outside ones. All right, so how many atoms do I have bonded to my central atom? 3. How many lone pairs do I have on that central atom? 2. 2 right here. 1, 2. Okay. And so this is what? T-shaped, and the angle is approximately 90.
What are the differences between the lone pairs on iodine and chlorine?
There isn't, but when you're trying to figure out your VSEPR structures, you look at the central. So that's why it says at the very top of that column, it says around the central atom. So it's whatever atom they're referring to. If we go back like last week and we had some structures that were like, you know, this, they would have to ask you, they usually call these C1 and C2, and they would have to ask you which atom they're referring to. All right. All right, bromine. Bromine is going to be our central atom. This is going to be 7 times 6 because bromine's 7 and fluorines are 7. So I've got 7 times 6 is 42 if I remember my math right. Okay. So I'm going to draw 5 fluorines around this bromine. I am. Yes, you are correct. It is Monday morning. Okay, let's try that again. All right. So right now I have 10 electrons. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 28, 1, 2, 3, 4, 5, 6, 7, 8, 39, 40. I did 40. What do I do? Add 2 to the bromine. Done. I'm up to 42. So we have how many around? 5. We have 1 lone pair. So this is square pyramidal, and it's approximately 90. Easy enough for Vespers. Catch it on to them. All right, I'm going to skip those. I want to go to polar bonds. If we have time, we can come back to those other ones, but I want to go to polar bonds. I think you guys get the idea of these, yes? Okay. All right, in order for a substance to be polar within the molecule, it has to carry different charges, and that comes down to electronegativities. Okay. Dipoles that are present must not cancel each other out due to symmetry. So this this drawing here, there is electronegativity difference quite a bit between the fluorines and the bromine here. Oh, but we do have a it's not a good one. Here, let's look at this one. Well, that has a charge though. That doesn't count either. I'll come back to that. Right. All right. So here, there's an electronegativity difference between the oxygens and the hydrogens. And remember that this has lone pairs of electrons on the oxygen here. Okay. So you can document this in one of 2 ways. You can use this S that kind of curls back on itself. It's a Greek symbol. It means charge, to show the positive end of that molecule and the negative end of the molecule. Or you can use one of these arrows where the arrow points to the negative end, and then you make the other end a positive symbol here. See how they did that with the slash through it? That end of the molecule then is positive. That makes sense how they kind of denote that? All right. Anytime you have a bent structure, anytime you have lone pairs of electrons on the central atom, you automatically have a polar molecule. Okay? So if you see lone pairs of electrons on the central atom and they're asking if it's polar or not, write down yes. You can just drop the mic. You don't need to consider anything else beyond that. You're done. Okay? So lone pairs of electrons on the central atom, you don't even have to give it any more thought. It's polar. Good? All right. So let's look at polar bonds versus polar molecules. So here we have silicone, and I've got 4 hydrogens around it. Oh, what is the electronegativity of silicone? Oops, and it's silver. Okay, so not a big electronegativity difference. Silicone is 1.9, hydrogen is 2.1. So the electronegativity difference here is 0.2. So these would be considered nonpolar bonds. And this is considered a nonpolar molecule, even if we had something out here like, let's just do fluorine, okay? So I want to change this up a little bit, and I'm going to change this to fluorine. And you're like, holy cow, that's a big electronegativity difference, because now we're going 4.0 to 1.9, right? So what is that? 10 minus 9 is 1. 3 minus, so that's a 2.1 difference. I mean, that's very dramatic. So these are polar bonds, but this molecule is going to be nonpolar. Why?
Symmetry.
Yeah, symmetry. So this comes down to symmetry. Okay, so the electronegativity difference is great, but because of everything being distributed evenly, it's going to end up being a nonpolar bond. Now, if we had something like this, now what are we going to have? Yeah, this is going to be a polar molecule. And your arrow would point this way, and that would be your positive. Now, it's a little easier to kind of see that in this format. They will draw this sometimes to goof with you like that. Now, this looks symmetrical, yes? But remember, we're working in a two-dimensional space here for a three-dimensional object. Okay, so when we look at that, we're going to have hydrogen. Homecoming's coming up. You guys are going to have to tie a lot of balloons for homecoming. I feel like every year I have to teach people how to tie balloons in here and light matches. Yep. I'm trying to make fluorine purple here in the balloon structure. Okay, so we're taking this, and this is actually going to have your fluorine and your hydrogen, but look at how much more space the fluorine is taking up versus the hydrogen. Okay, even though this is drawn like this and it appears that everything's symmetrical, these fluorines are taking up and have such a bigger charge cloud versus these. Does that make sense? So this is not a symmetrical atom. Now I replace these red with two more purple, and now all of a sudden it's all balanced out. That makes sense? Okay. So you have to look not only at the electronegativity differences with these, but you also have to look at symmetry. Okay. Here's another. Oh, what shape is this? Going back to Vespers. What shape would this molecule be? Tetrahedral. Bond angles? 109.5. Sounds like a radio station, doesn't it? Oh, do you guys even listen to like AM, FM radio stations anymore? No? Yeah. Okay, so the next one, we have sulfur here. I'm hoping that by now you guys are getting comfortable drawing Lewis structures, and I'm not spending a lot of time doing that. So hopefully you've had some practice with it. That's not pretty. Let's try to make that a little nicer. There we go. Okay, so polar or not polar? Polar. Don't even have to think about it. Why? Because the lone pairs of electrons on the central atom. What is my shape here? Mm-mm. No. Bent. Bent or V-shaped angle? 104.5. Okay. Polar, not polar. Non-polar because of symmetry. Okay. Shape. Tetrahedral 1095. And we just went through this guy. I got ahead of myself. It's essentially the fluorine one that I drew a minute ago. So you should be able to recognize now that this is going to be tetrahedral 1095, and this will be nonpolar. Everything's balanced out. It's found symmetry. It's got that balance. It's zen.
So the one on the right is balanced? Like it's like some, or are you talking about the one?
This one is balanced. This is found zen. This is unbalanced. This is going to be polar.
Yeah, I get that. So where would you put like the plus then?
Non-polar.
Yeah,
For this guy,
yeah.
You could draw it like this and this, and then this and this, I guess. I don't know that I would. If I had to draw this over, like I might redraw it and do this. And then I could clearly draw, then that would work. Okay. This is just kind of a hot mess the way it's drawn with the arrows, but this makes sense with the arrows, I think.
Yeah.
Yeah? Right. Okay. All right. Questions? All right. Let's talk about hybridization. So, hybridization is where, remember, we've been talking about these like 2s orbitals and 2p orbitals. We've talked about those, and we talked about our electron spin and all that stuff. Well, in reality, most of the time these hybridize. And so instead of having a hybrid orbit or an orbital that is sphere shaped for an S and peanut shaped for a P, or dumbbell, whatever you want to think of it, we end up hybridizing, and we end up with a hybrid orbital that looks something like that. Okay. So if we had a 2s and we had one of those, and we had a 2p and we had one of those, we would end up with 2 sp orbitals. Put 2 in, get 2 out. All right. Now, anytime, have we talked about sigma and pi bonds yet? Okay. So I think I'm getting ahead of myself then. So we end up with these hybrid orbitals. Okay. Now, the D block can hybridize as well, but they don't do that in AP Chem. That's for future science courses. I just throwing that out there to you so that when you get to college and they're like, and the D orbital hybrid, blah, 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 you know, and keep going, and you're like, what? I'm telling you about it now. It happens. We just don't talk about it in here. Okay. It's just too much to try to have you understand. Okay. But if you go out online, they'll talk about SPD hybridization and that sort of thing. So just be warned that it exists and it's out there. And if you really, you know, want to geek out and, you know, have a moment, yep, have fun. All right. So we can predict what kind of hybridization is going to exist, and they happen in different ways. Okay. We can have SP hybridization, SP2, and SP3 hybridization. SP2 hybridization, SP3 hybridization. And what you need to do is you need to look at what's called a sigma and a pi bond. Okay. I'm going to get into that in just a second. Let's see here. Yeah. I just need a slate here to be able to draw on. So when you have a structure that is just all single bonds. Those are sigma bonds, okay? And those bonds happen end to end. And you're like, what are you talking about, Libby? Let me draw, okay? So for example, if we have C carbon, let's do tetrafluoride, okay? You're gonna have your carbon in the middle here, okay? Your carbon is going to have, if we drew that out, it would look like that. Everybody cool with that?
Yes.
Okay. You got lone pairs of electrons. Oh. Okay, no, I want to go back. Thank you. Oh, why?
Happy Monday, Libby.
I'm very careful not to touch the screen with my hand. I don't know why it's doing that. Okay. So these are all single bonds around here. So every time you have single bonds, they're always going to be sigma bonds. They're going to occur side to side, and they're going to occur in hybridized orbitals. So sigma bonds always are in hybridized orbitals or your sp orbitals, okay? This is that sp orbital where we have kind of a central circle, and then we have one of these loops coming out. So you can kind of think of it as this coming together to form one of those. Does that make sense, the hybrid of it? Okay. So carbon has 4 sp orbitals coming out. I don't like that one. There. So those are my sp orbitals coming out of carbon. And then fluorine over here is going to have all sp orbitals, okay? They're going to attach to here end to end. So there's my fluorine. And then it's going to have 2 big lobes or 3 big lobes coming out of this side. And that's where your lone pairs of electrons are going to be. Okay. Now, you don't need to draw all this. I'm just explaining it to you. Okay. So don't get wigged out by this. You're never going to be asked to draw this ever in AP anyway. I don't know about college. I'm just trying to show you that this is occurring end to end. Okay. And that's where your sigma bonds are. And we would just duplicate that all the way around here. Okay. Does that make sense?
Sure.
I don't feel like that makes sense.
Is the middle one just yellow?
What?
Is the one you left carbon?
This is carbon. Yep. That's all carbon. Okay. Now, fluorine doesn't have any double or triple bonds, so it's going to have all these sp orbitals in it as well. That makes sense? All of its orbitals, all 4 of them are going to hybridize. So you've got this, and from that, you're going to get 4 of these. So this plus this equals this. This is your s orbital. These are your p orbitals. You good with that?
Yeah.
Okay. That's going to make these 4. 1, 2, 3, 4 makes 1, 2, 3, 4. Yeah? So for carbon, it's coming in. This is all my carbons. I've just arranged them so they look like a nice pretty flower. Okay. Now I'm going to attach a fluorine to it right here. Woo! Hello. Yeah. Uh-huh. Okay, so here's my fluorine, one of them. It's going to attach, this is a sigma bond here, attaching those 2 together, end to end. Good. That leaves me with 3 of these that I need to place around the fluorine, and they're going to be a little bigger because they have these lone pairs of electrons, which means that they're going to repel just a little more. And then I'm going to duplicate that for my next fluorine. And my next fluorine, sigma bond here. My next fluorine will come in over here. Sigma bond. And my next fluorine will come in here. Oops, no. Pedal there. There we go. Sigma bond and 3 more lobes coming out of here. Good? Is that making sense? So you've got 4 sigma bonds here. That's these single bonds that we drew with lines. Okay? Now, the way you figure out the hybridization is all you have to do is you have to look at this, oh God, this structure here, okay? Hold up 3 fingers and take 1 down for each double and triple bond. So you still have 3 fingers up, right?
Mm-hmm.
So this carbon is going to be sp3 hybridization.
What happens when there's 3 double bonds? Is that possible?
I don't think so, but let's get to getting here, okay? So let's look at these. Now, our pi bonds have to have p orbitals, okay? So if I drew this structure here, if I looked at carbon and my oxygens, so this is C. I want to go back to that other screen so I have a little bit of room to draw on. This was CO2, right? CO2?
Yep.
Breathe in, breathe out, breathe in, breathe out, CO2. All right. All right. You know, it would be nice if things just worked the way I want them to work, but they just don't. Today I came in and I could not figure out for the life of me why this thing wouldn't work. And it had extended the display over the weekend. So I had to figure that whole thing out and why. All right, so this is CO2. We said that its structure looks like this. Okay, so that's from the next slide. I just drew it over here so I could have a little bit of white space. I needed a little real estate here. All right, now this has double bonds. Anytime you have a double bond, you have to have a p orbital for that double bond to reside in. Because double bonds are side to side instead of end to end. Okay? And we can't do that with an sp orbital. So when we are looking at the hybridization of this first oxygen, we have to reserve a p orbital. So if we're looking at why? It went back. Okay. So if we're looking at that oxygen, okay, so this is my oxygen. I'm going to have an sp orbital for this sigma bond. I'm going to have an sp orbital for this lone pair of electrons and an sp orbital for this lone pair of electrons. But I have to have a p orbital for that guy. Double and triple bonds, the double and triple, the second one is called a pi bond. Okay, so the first one here is a sigma. So this one is sigma, that's the abbreviation for sigma. And this is pi, which I think you're familiar with that abbreviation for math. Okay, so I have to reserve a p orbital for that double bond. Good. So if I'm looking at the orbitals here, I'm going to have an sp, an sp, and an sp. But then I have to have a p orbital for that guy right there. We would duplicate that same thing for this oxygen. Does that make sense why they're the same? Now, my carbon, this is going to also be a p orbital. So for my carbon, I'm going to have 2 of them looking like this for my sigma bonds. That's for this bond right here and this bond right here. And then I'm going to have 2 p orbitals, one for this pi bond and one for this pi bond.
For oxygen, is that just one of the oxygens or both of them?
Both of them. Yep. I just said that it's going to be both oxygens. I just didn't bother to redraw it because it's the same thing. Make sense?
So is there 2 of those or just one?
Yeah, there'll be another oxygen on the other side here. So it's going to be this, this, this. That's for this sigma bond, and then these lone pairs of electrons.
Okay.
And then there'll have to be a p orbital here for that pi bond. Okay. Now, how does this look drawn out? My carbon, I'm going to have end to end here. Okay. That's going to hook up with my oxygen over here. That's my sigma bond. And then I'm going to have coming off of the oxygen 2 lone pairs of electrons. Lone pair, lone pair, lone pair, lone pair. Good. And then over here, I'm going to do the same thing. Sigma bond. That's this second oxygen here. Lone pair, lone pair. All right, what do I still need to place? My p orbitals. Okay, so I'm going to have a p orbital here from the carbon. And remember, these are side to side, not end to end. Sigmas are end to end, pi's are side to side. So this is the p orbital for that oxygen. And this is my pi bond here, where they connect. And I would duplicate that over here.
So sigma is side to
Side to side, which sigma, side, both start with S's. Okay. And then your pi bonds are here, and they are end to end. Now, ultimately, what you need to know is just the finger trick. Okay, but I wanted to just kind of explain to you what was going on, what they mean by hybrid orbitals, and that sort of thing. So let's do the finger trick here. Okay, so if we're looking at the hybridization of this oxygen, so we're just looking at this one oxygen here, and we want to know its hybridization. Hold up 3 fingers, take one down for the double bond right here, and what are you left with? 2. So the oxygen's hybridization is sp2. And this is what you need to know for AP Chem, for the exam. Okay? So the other stuff I went through, I just wanted you to have a background and kind of see it for...
So we don't need to
You're never going to have to draw those things. No. You're going to have to hold up 3 fingers. Okay? And for the carbon, you're going to take one down for this guy and one down for this guy. That leaves you with... Yep. And you don't write the 1 down. You just write down SP. Okay? That's it. That's all you got to know. And then this oxygen, what is its hybridization? sp2. Okay? Hydrogen doesn't hybridize. Why? It doesn't have any p orbitals. It can't. Okay? Carbon. This carbon right here. What is its hybridization? What about this oxygen? sp2. Okay? This carbon here.
SP2.
SP2.
sp3. Hydrogen can't hybridize. Doesn't have a p orbital. Trick question. All right, we talked about sigma and pi, and my whole discussion. Bond order, we've talked about that already. Yep, I got through it all. Tomorrow is mastery prep, y'all.
No, you shattered our silicon hydrofluoride. What do you call that?
Flippy, we're not doing the test tomorrow.